Now let's look at the problem of correlation. So suppose we have this data, height of people versus the weight of those people. So, this is just actually I randomly generated this data. This is hypothetical. So in general, taller people are bigger, so they have heavier weight. So there should be some correlation, right? So let us apply linear regression. So let's say height is x and the weight is y. So first we can apply linear regression like this. So y is equal to a plus bx, right? So this is height and this is weight. So if you apply linear regression to this data, then you should get, of course you don't have the exact data, so you cannot calculate, but I do have the data, so I calculated. And the value of A was found to be negative 99.8, and the value of B was found to be 0.937. So that was it. So this is y on x. So this is this line, this green line here. This line. Maybe I should use green. Okay. Uh, let's see. Green line here. But we can also model the height in terms of weight, right? So in this case, we treat y, the weight, as the independent variable, and x, the height, as the dependent variable. And you can also apply the linear regression. And if you do that, you would get the value of a prime of negative 0.995 and b prime is 0.215. And if you draw this line on this graph, then you get this blue line. So they are different. So which one is right? I mean, there's no point discussing, which is right or wrong. So if you apply one method, you get one result, and if you apply another method, you get another result, and that's it. But so maybe discussing, applying this kind of regression doesn't make sense because height depends on weight, weight depends on height. Actually, what happens is that both height and weight depend on something else, which determines height and weight, like the nutrition during growing up, and like also genetics. Uh, People with taller parents tend to be taller, right? So it's genetics. So there are many other factors. So just blindly applying linear regression doesn't make sense sometimes. So in that case, we are better off just analyzing correlation between two random variables. In this case, height and weight. So if we apply the linear regression like this, y equal to ab plus x, then if you remember, the coefficient b is given by covariance between y and x divided by the variance of x. And on the other hand, if you apply the linear regression in this way, x equal to a prime plus b prime times y, then by symmetry, b prime should be given by covariance of y, well, let's say x and y divided by variance of y. But covariance is always symmetric, so covariance of x and y is equal to covariance of y and x. So if you multiply b and b prime, what do you get? So this times this, you have covariance of x and y squared divided by variance of x and variance of y. And do you remember the definition of the correlation coefficient? So let's say R is the correlation coefficient. Then that was this. Covariance of x and y over square root of variance of x and variance of y. So if you compare this definition with this expression, you will see that this is equal to the square of correlation coefficient. What's nice about correlation coefficient is that it's symmetric, right? If you swap x and y, you still get the same correlation coefficient. So swap y and x, and swap y and x, y and x. Because covariance is symmetric, so this is equal to this. However, this is not the case for linear regression. For example, if you swap x and y, so compare this with covariance of x and y divided by variance of y. So this is completely different thing. Okay, so they are different. And indeed, this is equal to b prime here, right? So when there is, when it's the case where you cannot choose which one is independent and which one is dependent, it's often better to use correlation coefficient rather than linear regression and analyze the correlation coefficient. Now let's play with the correlation coefficient a little bit. We have just seen that this b and b prime is equal to square of covariance between x and y squared and variance of x and variance of y, which is equal to the square of correlation coefficient. Okay. And of course, b and b prime are the coefficient of linear regression. So that they are the slopes. Okay, and let's see. Y was a plus bx, and x was a prime plus b prime y. So these b and b prime are here. Now, can you see that? Can you show that r square can be also expressed as this: b squared, and let's see, variance of x divided by variance of y, which is equal to b prime squared and variance of y divided by variance of x. How so you should prove this. So to prove this, let's go back to the definition of b here. So b was covariance of x and y divided by variance of x. So this means covariance here can be expressed as b times variance of x. So you just replace this covariance in the numerator with b times variance of x. And same for this one. So why are these relationships important? Actually, they are quite useful for testing the significance of correlation coefficient. In fact, we can show that this quantity, so R is the correlation coefficient, and N is the sample size, number of data points, and divided by square root of 1 minus R squared. So this quantity follows t-distribution with n minus 2 degrees of freedom. So how can you show this? By the way, this 1 minus R squared is inside the square root, right? So this means inside this, R minus R squared should be always non-negative, right? Actually, it should be positive, but yeah. So can you show this is always true? In other words, R squared is less than or equal to 1, or you can say R is between negative 1 and positive 1. So this is always true. So if you try to calculate a correlation coefficient and found the value was greater than 1 or less than negative 1, then it's wrong. Something is wrong and you should correct your calculation. Well, anyway, let's go back to the topic. And so why does this follow the t-distribution with n minus 2 degrees of freedom? And does this sound familiar? We've just talked about t-distribution with n minus 2 degrees of freedom right before this. What was it? It was, it appeared, the same t-distribution appeared when we tried to test the significance of this slope, right? So let's see, what was it? Okay. So if you go back a little bit, before we have seen this quantity. X bar squared, and actually beta. So beta was the unknown ideal value of B, but in our null hypothesis, we assume that value is 0. So just erase this. And what was this S? So this S, was defined, S squared was defined by this large N squared divided by N minus 2, and this large S squared was the sum of errors or residuals, okay? So minus bxi squared. So this was the definition. So this quantity follows t-distribution with n minus 2 degrees of freedom. So actually, here and here, we are looking at the same quantity. So can you show this? Okay, in order to show that this expression and this expression are actually equivalent, it may be helpful to show, manipulate this s squared first. So, we want to get rid of this a first because, we know some relationships between the correlation coefficient and b, right? But there is no a here. So we want to get rid of this a from this. So actually it's possible to do this by using the sample averages. So s squared is this, yi minus a minus bxi squared. So this should be a little bit easier. So this can be changed to this expression, right? So if you use this, then it's easier to show that this is actually equal to this. So now look at this. This part, if you divide by n, so let's multiply both sides by, let's see, let's divide both sides by n. So s squared over n is n this, and b squared 1 over n x this. So this is the variance of y, and b squared, and this is the variance of x. Okay, so let's see. So if you factor variance of y out, you have 1 minus b squared variance of x divided by variance of y, right? And what's this? This. Okay. So this is variance of y, 1 minus r squared. So from this, we have small s squared as large n squared n minus, wait a minute, n minus 2. So let's see. So that is, so we have to multiply both sides by n again. So n v variance of y, or minus r squared divided by n minus 2. So let's put this s into, let's see, this expression. Okay. So that's t equals to b s, it was s, yeah, s square root of this xi minus x bar squared. Okay, so let's see. We replace this s by this, so we have b, that's square root, and v y 1 minus r squared and n minus 2, and this one. But you know, this looks like almost like variance, but what we are missing is 1 over n. But that 1 over n comes from here. Okay, so we move this n to here, it's 1 over n. So we have, this is variance now. Okay, so inside this is variance of x. So we have b square root of variance of x and divided by square root of variance of y, 1 minus r squared. And let's move this n minus 2 to the numerator. So, and let's see, what's this part? What's this part? That is, this part. Okay, r squared was this, so take the square root of this, you get b square root of this, and so this is r square root of n minus 2, and that's square root of 1 minus r squared. See? So this quantity and this quantity are actually the same thing. That's how we can test the significance of the correlation coefficient. So when testing this, what is our null hypothesis? In the previous case, for the testing of slope, our null hypothesis is that b is equal to 0. And if you reject this, then so b may be significantly different from 0, right? So in this case, if we translate b equal to 0 in terms of correlation coefficients, what's the null hypothesis? Okay, in this case, the null hypothesis is that the correlation coefficient is 0, right? So you can see this from this expression. This expression again. Let's see. This expression. If b is 0, then r is 0, right? If b is 0, then r should be 0. So the null hypothesis that b is equal to 0 translates into the null hypothesis that this correlation coefficient r is 0. So now we know that this quantity, once we know the correlation coefficient, follows the t-distribution with n minus 2 degrees of freedom, where n is the number of samples. Then yeah, we can apply t-test and see whether if this is significant or not. Alright, that's the end of this module. So congratulations if you finish all the lectures and tutorials and problem solvings and whatever effort you have made. Thank you all and see you sometime.